So in the following, we are going to deal with other two metrics, which are definitely different from the previous ones, because now with these ones, we are going to take into consideration shortest path between the nodes. And the first one is going to be closeness centrality, and the next one is going to be betweenness centrality. Okay, so let's start with this notation, which is Dij, which denotes the shortest path between node I and node J. Okay, I mean the length of that node, that path. And what we are calculating here is denoted by L sub I. Okay, so for each and every node I, we are calculating the shortest path, the length of the shortest path from to all the J nodes from this particular node I. We are summing this up and dividing it by n, which is the number of nodes. So what we are calculating here is an average distance from node I to all the other nodes. Okay, this average distance or average shortest path can also called as mean geodesic distance. Okay, so this is just an alternative expression for this. And the motivation behind is that in social networks, if we have a node with low mean geodesic distance, then maybe assuming that gossips or messages are spreading on shortest paths, which is obviously not necessarily true, then those with low value, low average value, they might find that their opinion or gossip or message get to the other people more quickly, or more so quicker than those with high average value. Okay, so we so far in centrality measures, what we have done is that if a node has a high value, then that is expressing that that the node is important. Okay, so if we are using, just going back to the previous slide, if we are using this equation, then an important node is going to have low value. Okay, so instead of having low value, we can of course take the inverse or the reciprocal of these averages and then simply get this expression here. So in this case, the important nodes which are having short mean distance from the other nodes, they will have higher value. And we can denote this with capital CI, and then this is called closeness centrality. And it's a very natural measure because, as we said earlier, shortest path can be really the way how messages or gossips are spreading, but of course other ways can also be it can also happen. But this is not the main problem with this metric. But let's see the next slide. So we know it from our background from algorithms and data structures that usually the shortest path between two nodes is kind of small. So we can say that it's proportional to the logarithm of the number of nodes. And this can also mean that basically this CI values, so the closeness centrality values, they are not very different from node to node. And if they are not different so much, then it can also happen that a small change, a very small change, just a couple of new edges or some new nodes with edges are coming into the graph, so the graph is in this way dynamic, then just by very small changes, the rearrangement of the closeness centrality ranking gets radically changed. And this is something which we don't really like, okay? But to demonstrate this, here is an example. It's actually a quite an old experiment, but it's still meaningful, of course. So we can take the famous IMDb database, which is the Internet Movie Database, and it contains a huge amount of information about movies produced well in the last whatever time interval. So we can get what kind of data we can get from that is actors and films, okay, actors and movies. And well, we kind of discussed this already, that of course that this one creates then a bipartite graph. In one part we have the in one group we have the actors of the database, and the other group we have the movies. And then an actor is connected to a movie if the actor plays any role in that movie. Now we can also do a projection from this graph, namely projection between, so a projection graph in which we have only actors, right? And two actors are connected if they ever played in the same movie. Now, of course, in this way, two actors can be connected multiple times. We don't count it. We can do it in a weighted way, of course, but I think in this experiment it wasn't done. And it turns out that if we do so and measure the closeness centrality values of the actors, then what we are getting is basically nearly 500,000 actors. And the first one, which is the top actor in with respect to closeness centrality, is Christopher Lee, a very famous actor actually, having 2.4138 as mean distance, okay, closeness centrality. And the second author is just different in the last two digits, okay? And then there are 500,000 actors, and the last actor, according to this ranking, has 8.6681. Okay, so if we take the division of these two numbers, so 2.41 divided by 8.66, then what we get is 3.6. So that's the ratio between the first author and the last author. Whereas 3.6, if we compare it to 500,000, then it's a huge difference we can see here. So I think it's maybe well. So I can't even count the the order of difference between these two numbers. So this experiment clearly shows that the closeness centrality is very sensitive for rearrangement or for changes in the graph, and this is definitely a feature which we don't really like. Now the other metric is called betweenness centrality, is somehow one of my favorites. And so basically the concept is that now again we are considering shortest path, and then we are counting how many times a node participates, or basically a node lies on a path between two other vertices. Only shortest path count, and we are still assuming that these shortest paths, they are playing role in spreading of information. And so vertices with high so this is going to be the betweenness centrality. Now vertices with high betweenness centrality value, they have impact in the network because if we assume that shortest path is the way how information spreads, then lots of messages passing through them, and also it's interesting to think about this, that if we are removing nodes with very high betweenness centrality value, they can really disrupt the communication between the nodes. Okay, but let's see how this can be calculated. Now this is not a very nice formula, I would say, but if you see it, then if you having a look on it, then it's going to be a very easy one. So let's start with this one. So GST, this is the total number of shortest paths between node S and T. Okay, so this is the this is counting how many shortest paths exist between two nodes. And here we have this other number, which is counting how many times a node I lies on the path, on the shortest path between node S and node T. And this is the ratio of these two. Now, of course, this could be 1 if in all the shortest path node I appears, but usually this is smaller than 1. Okay, it can't be larger than 1, of course. And we are summing this up for all S and T, node S and T, and this is going to be the definition of the betweenness centrality for node I. And it can be defined for directed networks as well. Could be a difficult one because there could be no no path between two nodes, whereas for undirected network, if assuming that the network is connected, we always have such a path. And another okay, so it's so for directed networks it's not really used. Regarding the sensitiveness of this centrality, we can consider that if we have a star graph which has only one node in the middle, and then it's connected to all the other nodes, and the other nodes are only connected to the central node, so we can call it a star graph. Now the central node of this graph has betweenness centrality equal to n squared minus n plus 1. And well, in this graph, what we have as a so in this star graph, a leaf has betweenness centrality equal to 2n minus 1, and if we are dividing these two quantities, what we get is roughly n over 2, which is a good number. So it's much better than what we got for the closeness centrality. So let's continue with the next slide, which is defining or somehow demonstrating the importance of node with high betweenness centrality. And we can take this kind of extreme case or extreme example in which we have a node here which is connecting two large groups of somehow connected nodes, and obviously this node A, it has very large betweenness centrality value because all the shortest paths between nodes in group 1 to group 2 and backwards, they have to go through this node A. So in this way, well, we can call this node as a broker. So in other centrality measures, this node A would not be very special because it's somehow on the periphery of these groups. And if you think about it, for example, the degree centrality value is only 2 of this node, and probably the eigenvector or the closeness centrality value is again not really impressive, but it definitely has a large betweenness centrality value, and it's definitely playing a role on the information spreading between the two groups. So if we are removing this node, then it has a huge impact on the graph. Okay, so on the next slide, we are just discussing briefly some variations of this nice between essentiality metric, namely the assumption that the information spreads on shortest path might not be true. So let's see that we have two other versions of between essentiality. One which is called flow centrality or flow between essentiality, which is based on maximum flow. So what is taken into consideration here is the maximum flow between the nodes. Okay, if you are interested in this, then please have a look in the scientific literature. And the other one which I would like to mention here is the so-called random walk centrality or random walk between essentiality. And here the only difference from the previous one is that instead of taking the shortest path between the two nodes or between the nodes in the network, now we are checking the number of random walks between two nodes and how many times a node I appears on these random walks. And of course, many times this random walk between essentiality correlates with the standard between essentiality, which is dealing with shortest path. And we can also say that if this centrality value is different from the standard between essentiality, then we can say that none of these variations are making too much sense.